main thing that I really didn't understand and now I understand well is that if you have something viscoelastic, buckling will amplify the viscoelastic effects because locally the strain rate in the hinge that buckles is much higher than that of a or comparable material that would have a comparable size that would not have such buckling elements, and so that means you amplify dissipation effects. So that was a surprise that came before we actually played viscoelasticity. But for instance, that means if you vibrate metamaterials and worry about vibration damping, you can absorb much more vibration than we thought you could because of this amplification of viscoelasticity, right? Or you can even completely cancel an instability if you shake too fast, for instance. And so that to me was surprising when we discovered it at the time. Take the Kirigami example. It's a very complex 3D shapes with nonlinear deformation and everything. And basically, the reduced model is first by asking what are the minimum modes of deformation I need to describe. The plates going out of the plane, right? And so that would be the way to. That's kind of the way we try to think about it. Like, what's the minimum kinematics that the object does, and then can you try to give it some energy penalty? Let's say like if you want to say I have two plates that bend. Well, how much energy does it cost me to bend? I am a researcher and teacher, a professor at the university, and my research sits at the intersection between physics and engineering. And so we try to basically explore concepts to blur the boundary between machines and materials, try to make materials behave more like machines, exhibit complex programmable mechanical tasks, using tools of physics. And so we try at the same time to have interesting conceptual tools that are relevant from the physics perspective, but at the same time have some relevance and usefulness as engineers would like. So we try to walk on that fine line, basically.
So I'm curious about the beginning, when you started working on this intersection physics and material here. Can you tell me about it's the beginning from there to think about this kind of problem to use physics and material? How would it start in this intersection?
I guess it started by seeing some of the very surprising materials that were already around, like people, the groups like Katia Bertoldi or Pedro Reis. They had these materials that had their buckling instability and somehow it was about being amazed by those things, not understanding what was going on, and somehow asking very naive questions and making as many mistakes as you could. And so it was about learning mechanics the hard way, and at the same time use this kind of naive approach to maybe ask interesting or questions that had not been looked at, or come with an angle that I think was maybe not yet taken, right? So asking the questions from the perspective of statistical nonlinear physics, which is my background. That was also the background of my postdoc advisor, Martin Laneke. And so we just try to, I guess, translate questions we would have had in the physics of granular material, like both he and I were doing before, to those materials with instabilities. So it was a very humbling experience, because you have to feel very stupid a lot of the time, but at the same time it was also a lot of fun, and it still is a lot of fun. But that's also what I'm looking at, I guess, things that put me in my stretch zone, I guess, where I don't really understand, I didn't really know. So I guess that's where I gain a lot of energy from.
Can you share some of this question, like back then, that maybe led you to what you do now? Like one of these questions, what was like maybe sound stupid at this time, but was really eye-opening for you to do something new? Do you remember any of these questions?
The first question, maybe the most basic, is you have an object that is made of it's a slab of rubber punched with holes, and then the main question is how should you think about it? What's the most basic way to think about it that still reproduces the fact that it has a negative Poisson ratio, the fact that it has a force, there's a load that increases when you start to compress, as in buckle, the load decreases a little bit, and then the question is, okay, what's the minimal way of understanding why there's a load that decreases at buckling? And so those were very basic questions in a way, and had we known about nonlinear mechanics, we perhaps would have overlooked some of them, probably, because some of those answers were maybe probably around. But then somehow coming up with these minimalistic models to describe those maybe allowed us to go a bit further and elaborate. Not only, I guess we started by asking, okay, is there a structure? How can I understand the property, right? So that's the usual forward problem, structure to property problem. And then from there, somehow, having devised very minimalistic tools, maybe traditionally in engineering are not adopted. Usually in engineering, maybe you want to use a more faithful description, using a more, like continuum beam theory and moderately slender theory like Mindlin-Reissner theory and so on. Instead, we just went for like the most basic approach, just a bunch of squares that connected by springs. And then somehow this gave us ideas to not only understand the structure property relation, but also do some design, like can you create materials that had on-demand shape change and so on, or on-demand force displacement curves and so on. So that was really, I think, was really a natural balance, I guess. First you understand, and then you try to design.
Maybe if we're going to the seam, that's what I'm interested about, your work about the geometric imperfection, origami, and this kind of line. I want to ask your perspective about soft robotics field in general. When you look to soft robotic field, do you think about the research line is going in the maybe more interesting path, whatever that means for you, like interesting path to understand how we can design complex structure like metamaterial to play with the hole in the beam, like that what you started with? Do you think we have enough of that research line, or do you think we're focusing on low-hanging fruits? What's your perception about the field, soft robotics, so far?
Yeah, I think I'm a bit of an outsider in terms of soft robotics. So to me, I'm always amazed by what people are able to pull off there and to do to really control. I mean, I guess there's interesting questions there. Is control the deformation, achieve very complex deformation based on very simple inputs. I guess that's what I see that metamaterials offer that opportunity. And so I feel like now, as I see, a lot of it is going into the control, right? Try to, reduce the number of control line, like fluidic lines where you inject your pressure, for instance, trying to achieve oscillatory behavior based on the continuous input. And so trying to get a single input, but multiple responses or multiple shapes based on just the history of what the pressure was. So I think there's a lot, and I think there's a lot going on there that I think is very interesting, connects more to this idea of multi-stabilities, going through pathways of, you have like a very complex, let's say, energy landscape, and the idea is to go to as many of the shapes, as many of the stable states as you can with just the smallest number of actuators that you have. And I guess what people call this embodied intelligence, right? That's kind of that's what I see. That's where I see maybe where soft robotics is going, or at least that's when I see the recent papers that I find stimulating are doing. And I guess what we are trying to do ourselves is maybe, I mean, sometimes maybe some of the concepts that we proposed when we looked at propagation of nonlinear waves, solitons could address some of those challenges as well. But for myself, I also like to keep this idea of material science, like propagation of a wave or something as a means, let's say, as an enabler.
Yeah, my question. Yeah, I think about asking this question because I was thinking about, since your focus about metamaterial and achieving intelligence in the structure, so playing with geometry, that's where I find it fascinating. Do you think this could be like helping other ideas? Like, let's give example, using, for example, self-healing and delaying damage. You can do this or this. So you can damage the material and self-heal, or make a structure that can resist damage. That's one of the examples that I'm quite familiar with. So that's why I'm asking, do you see what you do could tremendously help to reduce control, for example? You know what I mean? Diminish some thing that maybe we don't need. Maybe I'm wrong. I'm just curious from your perspective. Yeah.
Yeah, I mean, that's kind of the vision, is indeed create, I guess, do very dumb things to do smart functions, I guess. So yeah, I guess get the most out, the most complex advanced behavior out with the simplest building blocks, I guess, is with what we're trying to achieve. And maybe as physicists of soft matter, I guess, we try to harness or to use as much as we can the collective phenomena. And I think it could be very useful, in fact, because then if you get a structure or metamaterial robot that achieves more than the sum of its parts, indeed, I think that's useful, because then engineering the parts gets easier if they're simpler. So we have a paper or ongoing project where we say we reinvent the wheel. We have basic units that interact with a very specific interaction rule. They break action-reaction, they break reciprocity. And just by that, if you make a ring out of those or a material out of those, they just start to spontaneously roll. And so it's not like you have to program the sequence of actions such that the robots or the software distributed robot rolls. You just have to tell the robot break reciprocity, and then the robot would find by itself how fast it should roll, how much it should accelerate, what's going on if there's an obstacle, and so on. And so to me, I see a lot of mileage there for exploiting those nonlinear phenomena to get, let's say, autonomous adaptable response. And the reason is because if you use the material, typically a material is robust because of its distributed nature, right? And so if you can use distributed, let's say, emergent phenomena, that's collective phenomena, let's say, such as this example of rolling I was mentioning, then potentially you're more likely to be robust to, let's say, a failure in your control line or like an obstacle on route, and so on. And maybe that's this approach, exploiting collective phenomena, is maybe something that, I mean, people start to do that, but I feel like in soft robotics, you could do that even more, I think.
So I want to go deep dive in the geometric imperfection. And what I really like actually about your research, you're trying to define fixed laws, like the beam, for example, the other robots that you... So I think it's interesting the approach you're taking to, like, this is not fixated like the concept in physics. I think that's where you come with the physics background in robotics. Before going to that, the geometric imperfection, can you tell me how do you engineer the geometric imperfection to be functional and useful? Maybe it sounds for us, maybe, yeah, we're familiar about the instabilities and take advantage of the things, but I think the point I want to understand the process of thinking to take this geometric imperfection in design process. Can you tell me how you do that?
So basically, when we exploit an instability like buckling, if you take a kirigami and stretch it, there's 4 modes of buckling, right? And so if your object is initially perfect, there will be a spontaneous symmetry breaking, and your system will be in a combination of these arbitrary modes, right? And so which is not desirable, because then that means the shape that you get is not controllable, right? And that's typically what people have done in kirigami, is indeed try to well, either embrace or use the fact that these modes are there, or try to use curvature. For instance, if you take a sheet of kirigami and curve it, then indeed it will force one mode over the other, right? So you can think of curvature a bit as an imperfection. What we did was to use strain rate, the imperfection that depends on the strain rate. So basically, if you push slow, your imperfection would tend to create a kirigami that deforms into let's say, an anti-symmetric mode. But if you push fast, it will buckle into a symmetric mode. And then that means that you have a texture of the kirigami that depends on the strain rate, how fast you stretch it. And so what's interesting to me is that it's, I guess, in contrast with the curvature one, where you cannot really change the curvature of your kirigami on the fly. Here I can change on the fly the type of imperfection I use, either just by changing how fast I'm stretching the kirigami, or by just stretching and then waiting, and then by deciding by playing with timescales essentially. Yeah.
And I'm interested about the like for erased paper network communication, the kink, for example, in the kirigami. Maybe the question about the morphology and the configuration of the structure, the overall structure, how they all behave at the full scale and the smallest scale for geometry. How this had the relationship with when you play on the fly with the time scale to have different behavior. How that's much significant to design these shapes and geometries.
I don't know if we did much design there. We just made the kirigami, and then every unit of the kirigami has this strain rate sensitivity, right? And then that means that every unit, if you stretch fast, will go into, let's say, the anti-symmetric mode, and then if you hold the stretch shape but wait, it will cream back into the symmetric mode, let's say. And so that's really if you wish, that's really the physics of the single insert. That's the physics of, let's say, cream buckling, you could call that, right? I mean, and the cream buckling is a field that has been known already, right? But here we just applied it to kirigami. And then once you have, you have a collection of these elements that, kind of slowly or can creep back from one mode to the next, right? And that's the only thing we did was playing, just put many of them together, and then you ask, okay, if I stretch, how will the cream buckling occur? Like, will the cream buckle all together, or will it buckle in sequence? And what we found is that they indeed buckle in sequence. There's the first one that buckles if you push it, or if there's a tiny imperfection, and then the fact that the first one buckles, creep buckles, then will create a little push or torque on the next one, which will then go on and so on and so forth. And so indeed you have so that I guess the emergence of that kink, of that soliton that emerges, is really, I guess it's kind of a domino effect, if you wish, right? You could think of it a bit as domino in honey, right? if you think of it like that, you push the domino, it slowly falls, and then it triggers the next domino, and so on. So that at the end of the day, fundamentally, it really boils down to that.
I think what is interesting also the paper that you have that inspiration from a Mossa Bodica, that the sensitive blend. I'm curious, when you designed the kirigami, did you already thought about this inspiration at the beginning, like to design this unit?
No, it's something that came when we had this skink. We thought, okay, is there, so mimosa is a plant that, when you touch it also folds in sequence, and we just had this, and then we were, I guess it's the postdoc working with me, Shaham, who was just extremely creative, and we just realized, oh, by the way, I think I found an analog, or maybe we have a mechanical analog. So then he went on to play and put leaves on the kirigami to mimic it. So that was kind of a very playful moment. But yeah, indeed, it was really, I think it's him who came up. We just realized that it's very similar. And at the end of the day, we realized the equations that we used, the reaction diffusion equation, which is an equation that describes this, domino in honey phenomenon that people also use in chemistry. Is also an equation that people propose to describe the Mimosa pudica, also a traveling wave. And we were excited because somehow Mimosa is mechanical, so it's really shape changing of the plant. And besides that example, we're not aware of any other example, at least in synthetic materials, where you would have a phenomenon like this in a mechanical system. Maybe it also gave some inspiration because you have a plant that has a functionality. I guess it's to protect itself from a predator. It also means that maybe the plant acts as a basic machine, right? That responds to its environment and change its shape dynamically. That was also maybe an inspiration to kind of think about ways in which we could use our kirigami to achieve similar purposes, like reconfigure, change shape, transport an object, and so on. So indeed, the analogy with the plant was, I think, stimulating in many ways.
Mm-hmm. So I'm curious about the design also, because you use different material and multi-material in the design. So they make question about the selection of the material, and also when we speak about these spiral cuts in the kink in the origami, how also you make sure they don't fail, for example, or the limitation of the structures. Maybe that's the point I'm curious about. Yeah.
So this is again, all the credit goes to Sharam Yambas for he before he came to my group, he had actually also discovered, I think that's just thanks to his great creativity, that the materials that you can get off the shelf, the Connex object printer from Stratasys, are extremely viscoelastic, and we in the past. He and we in our group played independently with this, exploring, I guess, the consequence of this strong viscoelasticity on metamaterials and buckle. But he figured out that if you have two different materials of the shelf, the Tango and Agilus of that machine, they have slightly different viscoelastic relaxation. And so that means that one material is more viscoelastic than the other. That means that one material is stiffer when you go, they have the same stiffness when you stretch them slow, but one material becomes stiffer when you stretch them fast. One of those two materials. And so then he realized that you could use that to make to create this dynamic imperfection I was telling about. And then, I mean, we would have loved to have more freedom, but we were kind of limited by that machine, by the printer, because we are not polymer scientists. We were not really making on polymer. So, and so we kind of use that machine to the best of our ability, let's say. The polyjet printer, and of course the effect is there, but it's less present than if you mold. It's less present than if you compare like an ordinary polymer and this photopolymer, right? So if you take what Sharam had done in the past was to make structures that use this polyjet material. He actually ripped open the cartridge of the printer to mold it directly with just the ordinary silicone rubber. And there you get a very strong contrast between the viscoelastic properties of the material. It's very easy to get a strong response. If you want to make origami you have to texture it in a very specific way to see the dynamic imperfection. And then you cannot use casting. You have to really print. And then that means you're limited by the you're limited by the contrast in the viscoelastic property that you get. Which we were able to exploit to some extent, but I should hope that if you're able to tailor more of the viscoelastic property, you could do much more. You could have a much stronger response at the end of the day. And so, yeah, that's you could make thinner objects. They could carry more force, a lot. And then I think there's people, for instance, in the group of Julia Greer that are now also developing, more material scientists really that are really, I think, using tricks of material science. I wouldn't be able to tell the details, but to actually reach better contrast in the viscoelastic property of the materials. The idea of combining architecture, so the kirigami geometry, with material property, for instance, viscoelasticity, is and also you could, to some extent, plasticity. We also have work on using plasticity. I think there's a lot of opportunities there, and there's a lot of interesting science to be done, and a lot of I think there's a playground that is relatively unexplored, like to combine both. And so I see that it could be used. I think it could be used. We just scratched the surface, I think.
Okay, interesting. So I think it's one down the casting versus the printing techniques okay, interesting. So what other like surprising things happened maybe during this project or other project, like maybe surprising and was just define the law of physics? I don't know, did you find anything like interesting or you didn't expect?
So that, and maybe that connect to soft robotics or shape morphing, I guess. Yeah. Well, let me think for a sec. No, I understand when I first ventured that I didn't fully understand that. I mean, the main thing that I really didn't understand and now I understand well is that if you have something viscoelastic, buckling will amplify the viscoelastic effects. Because locally the strain rate in the hinge that buckles is much higher than that of a or comparable material that would have a comparable size that would not have such buckling elements, and so that means you amplify dissipation effects. So that was a surprise that came before we actually played viscoelasticity. But for instance, that means if you vibrate metamaterials and worry about vibration damping, you can absorb much more vibration than we thought you could because of this amplification of viscoelasticity, right? Or you can even completely cancel an instability if you shake too fast, for instance. And so that to me was surprising when we discovered it at the time. And yeah, I would say that the observation of this viscoelastic kink wave was also then surprising. If I now move on to, for instance, plasticity, which is also something we're exploring, there I guess I'm also, I mean, I guess maybe that's again it's a surprise that comes from my ignorance actually. It's just how much plasticity and buckling, how much the interplay between plasticity and buckling is interesting, and how much you can do there, right? So there's regimes of buckling, like for instance, one thing I really only recently appreciated is if you're usually you can buckle before you plastify, right? So your material is so slender, your structure is so slender that you start to compress it, it will buckle, and then only later you will plastify. Or if your structure is not very slender, you can plastify and then buckle. But then I think we rediscovered, it was there in the Hutchinson papers literature, that there's a regime that you plastify, and when you plastify, the elastic modulus becomes lower, and then this destabilizes your structure, and that makes you buckle. So you plastify, and that makes you buckle, and that creates a very strong asymmetry of stress in the structure that creates a negative slope at buckling, immediately negative, whereas all the other regimes have a positive slope. And so this is very good if you want to use plasticity as a way to create shape morphing or shock absorption. And so we have a preprint now where we showed that this localized buckling is very good if you want to make a very efficient materials that combine both stiffness and strength and dissipation, right? And we are exploring also how you could use that for like shape morphing, but you can only do the shape morphing once. So it will be shape morphing in the context of manufacturing, right? Where you start from a very simple kirigami in 2D and then you deploy it in 3D. And so that's also, I think, where it could be also a very interesting avenue for kirigami that has been exploited in the past in the context of stretchable electronics, the people like John Rogers and so on. But I think there's also an opportunity to exploit it in the context of kirigami for like engineering materials. So that's I think it for everything that concerns passive materials. Then I could also, if you want, to tell you much more about active materials. But then that's a bit different. So these are materials that we, as I mentioned it, we they are not made of static rubber unit cell. They are made of robots, of actuators, and sensors and Arduinos, and then so it's like kind of a robotic material, if you wish. And then the idea is that you could use as more. You have a feedback loop, a control. You can do control, distributed control at the level of every unit cell, right? And people use that or start to use that to take away energy vibration. So if you have a distributed control, you can take away vibrations. But for us, what we use those motors for is we use them to inject energy. And we inject energy in such a way that breaks this action-reaction, Newton's third law. Okay? And what's surprising there, I guess what was surprising when we didn't know anything about it is that if you create a material, we first started with chains and things like that, and we just had a paper published yesterday where we looked at solitons also in that chain. What's interesting is that because you break Newton's third law, you inject momentum in one direction, and this tends to create waves that are amplified in one direction. And so one surprise that came, for instance, from that's the paper of yesterday, we found that solitons are amplified in one direction, but also anti-soliton. And it's called non-reciprocal topological solitons in active metamaterials. And if you think about usual soliton, like the kirigami that we talked about, or the domino, you have solitons and anti-solitons will always move apart from one another. They will always, and if you think about domain walls in materials, it's soliton. When you drive the system, the soliton and anti-soliton will always move in different directions. Here, because of this non-reciprocity, we managed to make solitons and anti-soliton move towards the same direction. And so to me, that was surprising. It's maybe a new twist on soliton physics, let's say. And that means you could also potentially use it for whenever you need directionality, right? So if you want to make something that crawls, a soft robot that crawls, and that's actually already something we start to do, then that means you can send trains of soliton, trains and soliton and anti-soliton that only go in one direction. People like the group of, there's a Payou Science Robotics paper by Ahmad Rafsanjani on the crawling kirigami actu. There they managed to curl the kirigami, have it, and they had an actuator. And there, in some regime, I think you also have a soliton, right? But it's again a soliton that you have to reset every time, and so you have to stretch and unstretch your kirigami all the time. Imagine you would make a similar robot with this breaking of reciprocity. You could always continuously send trains of solitons and anti-solitons in the same direction. A bit like sometimes if you watch movies of millipedes, they have also trains of waves of millipedes going in one direction. Yeah. So to me that was a surprise, more from the perspective of let's say soliton physics. And now we are pursuing this kind of research essentially and try to apply it to robotic locomotion, right? So the question we're asking is, okay, how can you use this breaking of reciprocity as a means to create something that can locomote, roll or crawl in a robust way? And I guess here the surprise is that unidirectional, it's very robust. Whatever you do, it's always robust. You always have trains of, it can be soliton, it can be non-linear waves that are generated unidirectionally, whatever the shape of the material and in most circumstances. So I guess the surprise here is the robustness. Even if you switch as much as 50% of the robots, of the motors off, it still goes. And so to me, that's amazing. That you can achieve such level of robustness.
Maybe since it was end, I have a few questions. Maybe the question about the first thing about the interplay between the material and the structure you do. How do you see the material so much significant when you design? Like the limitation to make what you do, coming to its functionality, maybe that's the first question. And second question about the models and the computational models yeah. I saw that you mentioned the reduced model, so you don't take in consideration, if I understood, the whole physical things happening, or what do you mean by reduced model here? Yeah.
Yeah, I guess it's whatever we have access to with our machines. So no, we are not a 3D printing group, so we don't invest too much time in developing printing techniques. So we use off-the-shelf machines and off-the-shelf materials, and of course, we have got very good machines, but it's also limited. For instance, the Conex is very precise, very fast, and very reliable, but the materials that it prints are very viscoelastic and very they age, so they're not very durable. And so we use that. We use the Codex in prints that don't suffer much from fatigue, for instance. That was, by the way, a very hard limitation in the Kirigami King project, because we suffered a lot from lack of reproducibility and also aging of the material. If you look at FDM, FDM is great for material durability, but then it's not as good for accuracy and be able to do multi-material. We are now looking into solutions such as droplet-based thermoplastic printing. So some companies that do casting actually start to do that. And so we were starting to, not develop ourselves the technique, but buy the machine rather. And then at the same time, this gives you more freedom for the materials. But that's also a good thing of these thermoplastics. You have much more freedom. I would like, but I haven't done any effort in that area. What I would like to do is have access to, be able to design my material myself rather than just using whatever is commercially available. But you only have so much time, so I guess we don't do that. But I guess teaming up with people who do that would be great. Yeah. And then lastly, we use a lot also for Plasticity project, a lot of metal printing. This is by far the best in terms of accuracy in what you can print in the smallest feature size. But you also have other challenges. You don't have you need a support structure, so you're limited in the shapes you can make in terms of the complexity of the shapes. And of course, it's plastified, so you can only compress it once if you're interested about buckling. Yeah. So that's it and then when we look at these robotic materials I was mentioning, then it's not only printing. So here we use all our printers together, FDM, Conex, SLA. But then we have a lot of precision mechatronics to do. So we have to make our own coils and so on. And so there I would love to have to have printers that you can use to directly print an actuator or print a sensor or print an antenna, let's say, to harvest energy. And there I think you have the Dragonfly is a printer that allows you to do that, right? So we're also starting to look into that. But if you want to integrate, let's say, not only geometrical features and interesting kinematics in the materials, but also want to integrate, let's say, transducing of energy, right, in a way. That's really, I think, an interesting frontier, right? You could also think of other approaches like liquid crystal elastomers, things like, shape memory alloys to do that. So that's also, I think, an interesting avenue. But we haven't, that's also something we're thinking about. And I think there's also lots of potential to explore in that area, like how to, integrate even more the sensing and the actuation within the structure.
I was curious about the actuation, actually, because you mentioned about playing on the fly about strain rate for the Kinkis and the Kurokami. When you imagine the actuation, like what it looks like it's linear actuation. If we speak, this is in a future iteration, yeah.
If you would want basically a material with I would want that. I would want to make a material that mimics, animals. So we as animals have our own battery source of energy, I guess. Our actuators are muscles, I guess. So if I want to think about the materials that is the ultimate machine, I would want a material that has the ability to transduce energy and so to store its energy and transduce it. And so if I just look at the actuator parts, we only use electromechanical actuation, like a coil and a magnet, because at the scale at which we do things, that's maybe the most efficient. But it's hard to integrate within the structure, right? So I mean, you could integrate potentially a magnetorheological elastomer with some conductive coil that you would print around it to be able to mimic that, but I don't know if it would be the most efficient. So that's why I think other materials like let's say liquid crystal elastomers would be interesting, because then they typically can change shape and so on, but then you still need to drive them, and typically the way it's done is by coming with a laser or like a heat source from the outside to do that. And so in that sense, it's still far from something that's fully autonomous that can carry its own source of energy, let's say. And to me, that's, I mean, an interesting challenge. Like, how do you do that? Even the pneumatic actuators that people use in soft robotics are also often the energy source is a pump somewhere, right? A pump at the end of the day, what is a pump? It's just a magnet moving in a coil, right? It's electromechanical. It's electromechanical as well. And so if you want to do things at the centimeter scale, I think there's no way around. You need electromechanics to actuate something if you want an efficient mechanism. And to integrate this within the material, to me, is still an extraordinary challenge. That's if you take the perspective that you want the autonomous material, let's say, right? If you let go of that, if you're fine to put a laser or temperature source on the outside, then of course I think we're much closer.
Maybe quickly about, we will call it in, but the reduced model, quickly, for anyone listening, about, since you're coming from physics background, you mentioned reduced model. What exactly you reduce here?
If you take the kirigami example, it's a very complex 3D shapes with nonlinear deformation and everything. And basically, the reduced model is first by asking what are the minimum modes of deformation I need to describe, like, you know, the plates going out of the plane, right? And so that would be the way to. That's kind of the way we try to think about it. Like, what's the minimum kinematics that the object does, and then can you try to give it some energy penalty? Let's say like if you want to say I have two plates that bend, well, how much energy does it cost me to bend, or how much if you do viscoelasticity, is not the energy, but it's also like the torque response, the viscoelastic source response. And then if you have such a model, if you put many of them together, and if you assume that the deformations are not so different from one neighbor to the next, then you can potentially massage all your equations to a single partial differential equation that you can solve analytically. Right? And so if you do that, that means you kind of understand maybe the essence of the problem. And that's typically when I'm happy. So in a way, it's trying to find a model that is as complex as necessary, but as simple as possible.
So maybe the two questions left about, first one about the creativity. We mentioned creativity and I'm curious about when you have maybe the workload and saying, then how do you find this creativity to like working interesting problem, create a unique solution? I don't know what creativity looks like to you, and how do you make sure access such good quality problems and solution. I
think I'm very lucky to work with a great team of people. So I think most of the main thing I do, I think, is listen to the ideas. And then we also it's a collective process, right? We help, my group, they help one another select, what is an interesting, distill the interesting from the trivial, right? And so it's kind of a group culture, I guess, that I try to cultivate. But I'm very fortunate to be working with excellent postdocs and students who collectively do that, right? And the only thing I can do is indeed I guess, get more excited when I find an idea more exciting, and there's collective excitement. But the initial idea often comes from for instance, it was Sharam in the case of the Kirigami. It really was his idea, and then I'm there to help them maybe focus on maybe the questions that I'm more excited about, and then we find common ground. But I'm not the only one to do that. Everyone in the group actually contributes to that.
Maybe the final question, what I think is that maybe futuristic question that you wish your group to maybe solve, or you mentioned sort of a challenge, the material, etc., but maybe more quality, like hard challenges from physics and related to maybe soft robotics. Whatever it is, like something for you want to solve with your group,
So I think I would be very interested to indeed imagine a simple animal or like a cell collective that I guess can go through a complex terrain, fetch some food, remember where it's been in the past, and so achieve very adaptable, let's say, adaptable response. I would love to be able to achieve that, like create a material that can find its own source of food, let's say, and in a challenging and changing environment. I think would be to me an interesting question. So that's more kind of a there's no I don't know if anyone is waiting for that in terms of application, but I think you could potentially connect, and then that's one thing. And I think the process is very important. So while doing that, I think it's very important to me that we find interesting new scientific questions, like fundamental, basic questions that we that are explored. That's, I think, kind of on the short term where we're going. Then I also think those materials could help to some extent also to address some of the maybe more urgent challenges in terms of material circularity or scarcity and so on, or sustainability even. And so there, I mean, I'm not very strong in there, but it's always in the back of my mind. Okay, maybe it would be interesting to also see what we could do there, and some of our work on vibration and shock absorption, I think, could help there also, but it's maybe still a bit indirect. Yeah. So I would like also to explore, I guess, more concrete ways to make an impact in that direction.
This topic sounds very exciting. Yeah. Maybe I don't know if you have any final words you would like to say, maybe for soft robotic community. I know you're not exactly from soft robotic, but maybe for people of robotics and maybe general audience as well. Yeah.
Yeah, I mean, I really admire what the soft robotic community is doing. So I'm always very inspired and stimulated. So I guess my work is a word of encouragement. Keep up the good work. And then at some point there will, I actually enjoyed where there is sometimes convergence between what I do and then what the community does, and I look forward to exchanging and learning, basically.